This class, right, they don't have how many students?
Today about 7.
7. 7, 8. Thank you.
Good morning, everyone. Okay, let me some more people coming in. Good morning. Hi, Judy, Kayan, Monish, KJ. Can I trouble you all to turn on your camera so that later when we go through the materials, then I know whether you are still copying or you are done, then for me to better progress the lesson. Okay, Monish, camera is not working. How about Judy, Kayan, KJ? Okay, because now there's very few of y'all, so I hope that this lesson will help y'all to like revise these two topics as much as possible. So please turn on your camera. And also, if you haven't downloaded the material, could you please scan this QR code? And then it will lead you to Google Drive. Then you can download from there. If you already download, can you give me a thumbs up? Give me a thumbs up if you have downloaded the materials. Yes, does everyone have materials ready? I cannot, it say needs access. Okay. Oh, how about the rest? Let me. Ooh. Sorry, give me a while. Let me. Okay, I sent this link in the group chat. Can you all try whether the link can open? Okay, Monish can access already. How about the rest? Okay, try the link that I just sent in the group chat. Hmm. Okay, then I try to see if I can just send the file directly. Monish can access. Monish, which link do you use? Do you use the QR code or use the Google Drive link that I just sent? You use the QR code. Okay. Try to should be able to access it. Okay, for those who haven't downloaded, can you try with this QR code again? Hopefully it works now. Can someone let me know if the QR code works now? Yes, no? Okay, Ayan, thank you. How about the rest? KJ, Nick, are you able to download the materials already? Okay. Anyone still don't have the material? Judy, hmm. So I assume everyone has the materials already. If not, please let me know because I'll be starting now. Yeah, hello everyone. And so my name is, okay, I will start with the introduction first, about like 5 minutes, very short one. Then we'll go into the content. So my name is Sheila. I teach lower sec science and also IP science as well as upper secondary IP chemistry. So I've been teaching for 4 years. So most of all my students find my lesson very useful. And one fun fact about myself would be I'm an outdoor person. I enjoy like cycling, hiking, diving. So it's like activities on the land, in the sea, and also go up to the mountain. Yeah, so this picture is me going to diving, I think last year. Okay, so that's about myself. And moving on, okay, just a short introduction for Overmug. So Overmug is a established tuition brand in Singapore that we have 7 branches across different locations in Singapore. And now we have about like 5,000 plus students. Okay, and what can you expect if you decided to join OVERMUGGED in the future? So all of students will get a set of the OVERMUGGED curated notes, and then during the WA period, our tuition class will be doing topical revisions with the students, and mock exams is for major national exams lah. So I believe this one is an event kind of thing. It's not during regular classes, but our students can join as well. So for practical notes, hands-on experiment, we also offer experiments for topics like titrations, because titration you cannot just practice at home, right? So OVERMUGGED have these equipments to help our students to practice their practical skills. Okay, so that's about it for the introduction. Let me share screen. Okay, any questions so far? Okay, if your camera is working, please turn on your camera, because I only see all black screens now, which is a bit sad. If everything is okay, can you please give me a thumbs up so I know I can move on? Okay, thank you, Monish. Thank you, Karen. All the best. Thanks, Katie. Judy and Nick, everything okay? If everything is fine, then we will start with this atomic structure chapter first. Okay, so because of time constraints, I cannot possibly to go through every single concepts in these two chapters. So I'll be picking the most important concepts, then we'll go through in this 1.5 hours. So for atomic structure, the most important thing would be to know what is protons, neutrons, and electrons, and also be able to describe the structure of an atom. Means like what is inside a nucleus and what is in the electron shell. On top of that, we'll also be revising about how do we write SPDF electronic configurations for the elements. Then we'll also talk about the nuclide notations, and lastly, the isotopes. So far, is there any can I know which one would you all like me to focus more on? Is it the nuclide notation? Is it the isotopes? SPDF notation? So that I know roughly which area you all are need more help in, so that I'll be slower in that section. Can type in the group chat nuclide notation, isotopes, or is it SPDF? Can I have some response? SPDF, okay, isotopes, can. Okay. Okay, then I will focus more on that. What is isotopes? Okay, so firstly, we have to understand what is inside an atom. So inside an atom, there are 3 subatomic particles, which is the electrons, protons, and neutrons. So where is their location? Where can you find them? Protons and neutrons would be found in the nucleus. So nucleus is the center of the atom, and inside the nucleus, we will have protons and neutrons. Okay, so that is the center. And then around the nucleus, around the center, there is electron shell. So in this picture, this would be the first electron shell. And the maximum number of electrons we can have in the first electron shells would be 2 electrons. For the second shell, the maximum number of electrons would be 8. Maximum 8 electrons. Okay, so protons and neutrons found in the nucleus. Electrons will be in the electron shell. In the first shell, we got 2 electrons. In the second shell's maximum, we can have 8 electrons. So what is the protons? What is the neutrons and electrons? So protons is a particle with a charge of +1. So how I remember is like proton is like pro, you are very pro. So the charge is +1. And for neutrons, it sounds like neutral, right? So the charge would be 0. And then for electrons, would be -1. So when you write the charge, make sure you put the sign in front. So -1, okay, not 1 negative. Because we want to know about the charge. So you need to tell me what is the sign first instead of the number. Okay, so that is for charge. For relative mass, the majority, okay, a big part of the mass of the atoms comes from neutrons and protons because their mass is, relative mass is 1. But for electrons, is 1/1836. Okay, you don't need to memorize this number. We just need to know that electrons, the mass is like very, very small. So 1/1836 is 1 divided by 1836. So I think that will give you what? 0.00 something, which is very small. So the mass of the atoms comes mainly from the protons and neutrons because their relative mass is 1. Okay, and then the symbol is as such. Proton will be P, neutrons N, electrons will be E. I think these are quite straightforward. Okay, and then location we have already went through just now. Okay, so what we have, what I want to emphasize here is when we talk about atoms has no charge. So overall, the charge of an atom is neutral. So how is that possible? We know that there's protons with a charge of +1 in the atom. Neutrons has no charge. Electrons has -1. So overall, for an atom to be electrically neutral, I must have the same number of protons and electrons. Okay, so this is what the sentence is saying here. As the number of positive and negative charge in the atom are equal. Or you can also say the number of protons and electrons in the atom are equal. So the atom is electrically neutral. Okay, so because later we'll be talking about ions, which is not electrically neutral, that's electrically charged. So for now, I need you all to remember that atom is neutral. And that is achieved by having the same number of protons and same number of electrons. Okay, then the next part will be about the periodic table. So I believe you all have seen periodic table. And I just want to highlight a few important numbers that you need to know, like what is their meaning in the periodic table. So you see periodic table, there's these elements arranged in sequence, right? 1, 2, 3, 4, 5, 6. So, and so on and so forth. So this is like the index number of the element. So for hydrogen, the index number would be 1. It's just like in class, we also have index number, right? Index number 1 to the last person in the class. So same thing for our elements here. Each element will also have their own index number. So, and this index number, we call it the protons number or atomic number. Okay, proton number / atomic number, they mean the same thing. So it's referring to the index number of the elements. And this number can actually tell us the number of protons that atoms have. So because just now I mentioned that there's like index number for the different elements, right? So this index number is the number of protons of the elements. So as long as you have, for example, 2 protons, the element will confirm be helium. Okay, so what elements is determined by the number of protons, which is the index number. So far, is it clear? If it's clear, then give me a thumbs up. Okay, thank you, Monish. How about the rest? Okay. Yes. So for atoms, because it's electrically neutral, and hence the number of electrons must also be the same as the protons, because atoms is neutral, so protons and electrons must be the same number. Okay, and when it comes to nuclide notation looks like this, and we have 2 numbers, one on top and one at the bottom. So the number at the bottom would be the index number. So it's usually the first number that we will look at. So when you see this, immediately you know that, okay, there is 12 protons. Okay, how about the number of electrons? What would be the number of electrons in a magnesium atom? This is Mg. So Mg stands for magnesium. Okay, what is the number of electrons the magnesium atom has? If you are too shy, you can type down your answer in the group chat. Then I will see from there. Okay, what is the number of electrons? Okay, 12. Okay, 12. Okay, most of you say 12. Yes, because it's an atom, so protons and electrons number must be the same. Then the last one, our last subatomic particles for the neutrons, we can know the number of neutrons from the number on top here. So the number on top here is called the nuclear number or the mass number. It's basically the number of protons plus neutrons. So just now, we know that our proton number is 12, right? And since the total must be 24, it means that our neutrons number must be 12 also. And this is called the nuclear number and mass number. So why mass number? Because just now I mentioned that the main, the large amount of mass of the atom comes from the protons and neutrons, right? Because their relative mass is 1. That's why it's called mass number, which is protons plus neutrons. Okay. So that's for atoms. And then moving on to ions. What is an ion? So just now we start with an atom, right? For example, like this sodium atom here. This is Na is sodium atom. And then what you see over here is the number of electrons in the electron shells. So total there is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 electrons in a sodium atom. Why? Because you look at the periodic table, the index number of a sodium is 11. So it means 11 protons. So atoms is neutral, it means that sodium atom must have 11 electrons. So this structure is not stable because I only have 1 electrons in the outermost shell. So the atoms will want to lose that 1 electrons. So donate away that 1 electrons. So atom loses electrons to become positively charged. And when it's positively charged, when it becomes a positively charged ions, is called a cation ions. So in a cation ions, the number of protons would be larger than the number of electrons. So this is something that is different from atom. Atom is protons equals to protons equals to electrons. But for cation ion, I will have more protons than electrons. Okay, but for sodium, the proton number will not change. The proton number will still be 11 because this is the index number of sodium. Index number will never change. What will change is the electrons. So sodium atom has 11 electrons. When it loses 1 electron to become a sodium cation ions, then there will only left 10 electrons in the sodium cation ions. So this is for cation ions. So metal tend to lose electrons because metals, look at the periodic table. Okay, the first, the ladder is here. So everything on the left side of the periodic table would be metals, and then on the other side would be non-metals. So for metal atom, they will tend to lose electrons because the number of valence electrons is smaller. So for example, the group number here tells us the number of valence electrons. Group number is the number of valence electrons. So it's easier for the metals to lose 1 valence electrons to achieve the stable noble gas configuration, which is either 2 electrons in the first shell or 8 electrons in the second shell. Whereas for non-metal, for example, like nitrogen, the number of valence electrons that it have would be 5 valence electrons. 5 valence electrons for nitrogen. So is it easier to lose 5 valence electrons to become stable, or is it easier to gain 3 electrons to become stable? Okay, if you think it's lose 5, can type in the group chat lose 5. Or do you think it's gain 3 more electrons to become more stable there? Okay, good. Thank you, Kayan. They gain 3 electrons. Correct. So that is what happens when the atoms, so nitrogen atoms, can gain electrons to become negatively charged. In this case, if I have nitrogen atom, it will gain 3 electrons to become a nitrite ions. So become negatively charged. And negatively charged ion is called an anion. So can you all please tell me, so for nitrite ions, N3 minus, what would be the number of protons and number of electrons in N3 minus ions? Okay, what is the number of protons? Number of protons. How many protons in the nitrite ions? Any response? Okay, type in the group chat. 7. Okay, how about the rest? Please type down your answer so that I know whether you understand what I'm talking about. 10. Okay, so proton number proton number is like the index number. So for nitrogen, in the periodic table, the index number for nitrogen is 7. So index number will never change, right? Regardless whether you are atoms or ions. So for the number of protons, it should be 7. Okay, but thanks for trying, Monish. So proton number equals 7. How about the number of electrons? So now we know that for the ions to have a charge of 3 minus, it means that the number of electrons must be larger than the protons, so that the overall charge would be negative. Because electrons have a charge of -1, right? Proton is +1. So overall, if it's -3, it means that I need to have 10 negative charge. So 10 electrons in a nitride ions. This is how we usually phrase our answer. We say atom gain how many valence electrons to form a cations. So why would they want to gain, so it should be gain valence electrons to form an anion. Okay, so I think the sequence here is a bit jumbled up. If you are gaining electrons, you should become an anion. If you lose the electrons, you should become a cation. Okay, so why would atoms want to gain electrons? Because they want to achieve stable normal gas configuration. So for example, nitrogen atom, initially they got 5 valence electrons. They need to gain 3 more to become 8. Then that is a stable normal gas configuration. Okay, KJ has a question. Does carbon atom gain or lose 4 electrons to form normal gas electronic configuration? So carbon atoms, they will tend to... So carbon atoms, they don't lose or gain. They share electrons. So this one we'll talk about it in the next chapter in covalent bonding. Okay, because carbon atom is like in the middle, it's equally hard to lose 4 or gain 4. So they don't lose or gain. They share electrons with another atom. Okay, I hope that clarifies. Okay, then for the electronic structure, this would be the SPDF configurations. So electronic structure, we are talking about the principal quantum shells inside the atom. So inside the atom, we have okay, let me write this down. Principal quantum shell. So inside an atom, it consists of nucleus and principal quantum shell. So inside the nucleus, we have, okay, so contains protons and neutrons. And inside the principal quantum shells is made up of subshells. And within the one subshells is further made up of the orbitals. And finally, inside the orbitals, it contains electrons. So these are the 3 subatomic particles that we are talking about. So electronic structure is for the electrons. Okay, I have Kaya asked me a question. What is SPDF? Okay. Kaya, because I think SPDF, only some school teach about SPDF. So if your school, you didn't learn about SPDF in school, then you can just listen for this class. Yeah, because every IP school, the content is slightly different. Okay, so SPDF is referring to the name of the subshell. So principal quantum shell is made up of subshell. Inside the subshell is made up of orbitals. And we need to know that for the first electron shell, only have one subshell, that is 1s. Okay, just now we have an atom, right? Which contains the protons and neutrons. And then we have first electron shell, second electron shell. So for this first electron shell, there's only one subshell that's called a 1s subshell. Then followed by the second shell. The second principal quantum shell is made up of 2s subshell and 2p subshell. So on and so forth. Third principal quantum shell, we have 3p, 3s, 3p, and 3d. So I think, okay, let me try to make it clearer by showing you some examples. It actually is very simple to understand. So for example, like my helium. Okay, helium atom, the number of electrons would be 2 because the proton number is 2. And then being an atom, which is neutral, the electrons number must be the same. So 2 electrons also. And where can I find these 2 electrons? So these 2 electrons can be found in the 1s subshell. So how do we fill in this subshell? Is by the energy level. We will always fill in the subshell with the lowest energy first. So the lowest energy would be 1s, followed by the 2s subshell, 2p, 3s, 3p. So if I have 1 electrons, then the electrons will go to the 1s subshell. Okay, so I will write 1s1, which is like what is given here for hydrogen. So 2 electrons, I will continue to fill up the 1s subshell because each subshell can have 2 electrons. So for example, like carbon. Carbon would have 6 electrons. So first I will fill up the 1s subshell first. S subshell can hold 2 electrons. And then proceed to the next energy level would be 2s. This one will also have 2 electrons, followed by 2p. So total I only need 6. So there will only be 2 electrons in the 2p subshells. And so okay, so electronic configuration is just filling up the number of the electrons. And another way to look at it would be using the electron inbox diagram. So the sequence is, we always start with 1s subshell. And 1s subshell can have a maximum of 2 electrons. 2s also have a maximum of 2 electrons, followed by 2p. 2p will have 3 orbitals as written over here. So 3 orbital means like under 2p there will be like 3 boxes, and then each boxes can have 2 electrons. So the next energy level would be 3s, 3p. 3p will have 3 boxes. Okay, so we can fill in the number of electrons accordingly. Maybe I use, for example, chlorine. Chlorine have 17 electrons. So I will first fill in 1s subshell because it's the lowest energy level. So 1, 2 electrons, 3, 4. And then for the 2p, for the 3 orbitals, how we fill in? We will fill in all the box in a single for single electrons. So we don't pair them up yet. So let me label. This is the first electron, second, third, fourth, 5, 6, 7. Then now they got no choice already. Electrons will not want to stay together. Why? Because all of them are negatively charged. So once they will only be paired up when they have no choice. So the 8 electrons would be paired with the 5th electrons. And then 9, 10. Okay, so far we already have 10 electrons, but we need 17. We will continue to fill in the box. 3s will have 2 electrons, so this will be the 11 and the 12 electrons. And then 13, 14, 15, 16, 17. This is 17. So when we write the electronic configuration, it will be 1s2, 2s2, 2p6, because I have 6 electrons in the p subshell. Then 3s2, 3p5. Okay, so you can see it's the same as given in the table here. Okay, any question? If you have question, please type down in the group chat. Okay, if not, then I will move on. Okay, I will skip the part for the SPDF for ions and transition metals because it's not very relevant to some of the students. Okay, and the next thing we'll talk about would be isotopes. So what is an isotopes? Can you put a 5-star on this paragraph? Die must memorize the definition of isotopes. So isotopes are atoms of the same element with the same number of protons, different number of neutrons. So as long as I have atoms that have same number of protons, but neutron number is different, so these two pairs will be called an isotopes. So for example, if I have a chlorine 37 and chlorine 35. So the proton number for this be 17 because the bottom number tells us the proton number. Same thing for this one. What would be the neutron number for the first chlorine? Can you type down in the group chat? What number should I write over here? Okay, 20. Yes, because 37 minus 17, that will give us 20. Then for the chlorine on the right side, be 35 minus 17 equals to how much? 18, right? Yes. Okay, so in this case, we can see that both chlorine have 17 protons, but for the chlorine on the left side, 20 neutrons. On the right side, I have 18 neutrons. So these two atoms, they are called isotopes because they have the same number of protons but different number of neutrons. Let's talk about some properties of the isotopes. So these two isotopes, they will have identical chemical properties. Means that they will undergo similar chemical reaction because they have the same number of valence electrons. So the valence electrons will determine what kind of reactions that the atoms can undergo. As long as they have the same number of electrons, then means their chemical properties will be identical. Whereas for physical properties is referring to like density, melting point, boiling point, not chemical reaction related. Then isotopes will have different physical properties because physical properties is determined by their mass. Okay, can you highlight because they have slightly different mass? Physical properties is affected by the mass. So different mass will give different physical properties. So why is it different mass? It's because the number of neutrons is different. Remember the mass just now is mainly made up of protons and neutrons. So isotopes will have different physical properties. Okay, let's go through this one. Okay, so for isotopes, we actually can calculate the atomic mass of the atoms if we know the percentage abundance of the isotopes as well as the mass number, which is 35 and 37 over here. So how can we calculate that? We will take the percentage abundance, which is 75%, multiplied by the mass number of the first isotope. Mass number of isotope 1. Okay, then we plus the percentage abundance of the second isotopes multiplied by the mass number of isotope 2. So the relative atomic mass, you can actually see this as the average mass of all the isotopes of chlorine. Because I'm just taking the fraction multiplied by the mass plus the percentage fraction multiplied by the mass of the second isotopes. Then it will give me the average. Okay, this is also important, this calculation. Okay, is it clear? If it's clear, then give me a thumbs up. If it's not clear, then type down your question and let me know. Where is your doubt? Okay, is everything okay? Okay, thanks, Wanish. KJ, Nick, are you there? Judy? Hello? If you are there, give me a thumbs up. And if you have a question, then type down your questions in the chat. Okay, we will move on to some to the practice questions. Okay, so for question 1, I have an ions of element X with the formula of X 3+ that has 18 electrons and has a nuclear number of 45. So how many neutrons are there present in the atom of X? Okay, so how can we approach this question? Firstly, we have X 3+, and then we know that it has 18 electrons. So how many protons would element X have? We know that the charge is +3. So for the charge to be +3, and when we compare the number of electrons and protons, the number of protons should be more than 18 or less than 18. Okay, what should be the number of protons? Okay, thank you, Kaya. Okay, 21. Yes. Okay, because to have a positive charge, my proton number should be more than the number of electrons. And now we know that there is 21 protons, and we have a nucleon number of 45. So nucleon number is made up of protons plus neutrons. So if protons is 21, then neutron must be 45 minus 21. That will give us 24. So the answer for this question would be B, boy. Okay, for question 2, which atom has a half-filled p subshell? So this question is testing on the SPDF notation. So for neon, Ne, which is neon, let's check what is the number of electrons that a neon atom have. So let's look at the index number of neon, 10. So it means in my SPDF notation, too much. Okay, I should fill in 10 electrons. So 1s, 2s, 2p. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So option A will not be the answer because my 2p subshell is fully filled, it's not half filled. Then moving on to option B. P, again, we go to check what is the index number or the proton number of P. P is phosphorus, is found here. So 15 is the index number of P. So means that phosphorus would have 15 electrons. So similarly, we also fill in the electrons. After 2p would be 3s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, not enough. Need to add in another 3p subshell. 13, 14, 15. Okay, so you can see that the p subshell is half filled over here. So option B is the answer. Okay, of course you can go and try option C and option D, but the SPDF notation for F would be 1s, 2s, 2p5. Right? Because fluorine need to have 9 electrons. So 5, 6, 7, 8, 9. Okay, and the box will look like this. 2s, 2p5. So this is not half filled also. Then for oxygen, there is a total of 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. This one is also not half filled. Okay, so confirm that the answer is B. Next question. Which particles are isoelectronic with one another? So isoelectronic means same number of electrons. So this is testing us on the nuclide notation and how do we read? How do we find the number of protons, neutrons, and electrons in each of these notation? So for the first one, Q over here, the bottom number is the index number. It means that it's a proton number. So we have 8 protons. And then neutrons, we will be taking 14 minus 8. That would be 8 neutrons also. Okay, 14 minus 8 because this is the mass number given over here. For number of electrons, the charge is negative. It means that I need to have more electrons as compared to my protons. So I got 8 protons here. In order to have a charge of negative 2, means that I must have 10 electrons. And then for the next one, R, I will have 10 protons. Neutrons number would be 19 minus 10. That will give us 9 neutrons. And then for electrons, it would be the same as the number of protons because R, this one is an atom, don't have any charge. It's a neutral charge, so the number of protons should be the same as number of electrons for an atom. Okay. So I won't go through the rest, but I will just go through this one, the one with positive charge. Because it's very similar, like for the atoms, R and T, and then, yeah. So for positive charge ions, it's the same thing. The bottom number tells us the number of protons. So 11 protons, and then neutrons will be 23 minus 11. This will give us 12. And number of electrons, because this is a positive charge, means that I will have more protons than electrons. So electrons must be 9. Okay, the answer for this question will be option A. Okay, for question 4, okay, which row gives us a possible number in a positive ions of isotope T? So T have P electrons and N electrons. So being an isotope, it means that I must have the same number of protons, different number of neutrons. Because that is the definition of isotopes, right? So for protons, I must have the same number, P also. So option A is up. Different number of neutrons. Neutrons cannot be N anymore. So option B is also up. Then electrons. How many electrons should the isotopes have? So electrons, remember, depends on the charge of the ions. So now that we know that the ions has a positive charge, it means that the number of protons must be bigger than the number of electrons. So that the overall charge will be positive. It means that the number of electrons must be less. So that will only be possible for in option D. Okay. For the next question, define the term isotopes. Okay, this I can just copy from the notes. Okay, but make sure you have this phrase, atom of the same element, have the same number of protons, different number of neutrons. Okay, for question B, why the relative atomic mass is not a whole number? So relative atomic mass, as we mentioned just now, atomic mass is simply just the average mass of all the isotopes. So when we take average of something, it's actually quite unlikely that we will get a whole number. Okay, so that would be the answer for this question. Okay, can you just take a screenshot of the answer? Okay, 3 seconds to take screenshot. 3, 2, 1. Okay. Move on. Question, part C, calculate the relative abundance and the mass number of the fifth isotope. So there's two tasks for us to do here. First, to find the relative abundance. Second one is to find the mass number of the fifth isotopes. So let's look at figure 5.1. Okay, figure 5.1 on the x-axis here is the mass number. So for isotopes with a mass number of 90, for isotope with a mass number of 90, the relative abundance would be 51.5%, and all these other isotopes respectively. So isotopes with a mass number of 91 have 11.2% of percentage abundance. So these are the 4 isotopes, and then now our task is to find the 5th isotopes. Okay, so the relative abundance of all the isotopes should always add up to 100. So we take 100 minus by the relative abundance of the other 4 isotopes. And that will give us 17.4. So if you get this would be 1 number. And to find the mass number of the 5th isotopes, we will use that formula. You know, the percentage fraction multiplied by mass number, then we add all of them together. So same thing over here. It's just that now we have more isotopes now. We have 5 isotopes in total. So we will take the relative abundance of the isotopes with a mass number of 90, multiply them together, then we add for the second isotope, third isotope, fourth isotopes. And for the 5th isotopes, we do not know the mass number. So we'll just put an unknown Y first. But we know that the atomic mass is 91.2 as stated in the question. Okay, the question should have mentioned that the atomic mass of zirconium is 91.2. If not, it's not possible to find. Yeah, they should have another line here. Atomic mass of zirconium equals to 91.2. I think I missed out that line when I said the question. Okay, then we rearrange the equation to make y the subject. Then we should get 93.3. Next question over here. SPDF notation for ZR. If we refer back to the periodic table again to look for the number of electrons of ZR, ZR is over here, 40. So total, I need to have 40 electrons. So after 2p6 would be 3s, 2 electrons, followed by 3p. P subshells can have 6 electrons. Then 4s2, 3d10. D orbitals can have 10 electrons. Okay, so this is from notes page number 6. We will fill in the first 1s first, followed by 2s, 2p, 3s, 3p, and then 4s first, because 4s has a lower energy level than 3d. Then 3d would be the 7th one. 8, 9, 10. Okay, I will move on because we are running short of time. For chem bonding, I will just be focusing on the covalent bonding, which is this one and this one. Okay, so first let's start off with ionic bonding. How would we get ionic bonding? Is when I have a metal bonded with a non-metal. So non-metal will donate, because metal will donate electrons to the non-metal, because metal tend to lose electrons and non-metal will gain the electrons. So when they do this transfer of electrons, they form ionic bonds. And this is the definitions of ionic bond: strong electrostatic forces of attraction between the oppositely charged ions. Okay, meaning that I start with Na atom and, for example, oxygen atom. And then Na atom, which is a metal, it will lose electrons. For the non-metal, oxygen, it will gain electrons. Then together, they become Na plus ions and O2 minus ions. So between these two ions, there is electrostatic forces of attraction. Besides electrostatic forces of attraction, oppositely charged ions form ionic bonds. So why would they want to do this? Why would they want to lose electrons, gain electrons? So is to achieve stable noble gas configurations. Because non-metal and metal, they will not just want to lose electrons or gain electrons for nothing. Right? All this is to achieve the stable noble gas configuration. So this is just for one ionic compound. So we have Na. We have Na plus and O2 minus. So together they will form a sodium oxide compound. This is just one sodium oxide. So if we have many sodium oxide, they will form this structure called a giant ionic lattice structure. Okay, let me write down the name. If I have many ionic compound, then they will form a structure that is called giant ionic lattice structure. And the most important concept that we need to know about the structure would be how do we explain the physical properties. So usually melting point, boiling point is commonly tested, as well as electrical conductivity. So for giant ionic lattice structure, which looks like this, I have positive ions, negative ions arranged in fixed position. This is negative. They will form these ionic bonds between the oppositely charged ions. Okay, or we call it electrostatic forces of attraction between the oppositely charged ions, EFA. And these bonds is very strong. So a lot of energy is required to overcome strong electrostatic forces of attraction. Between the oppositely charged ions. So if the question asks you, why sodium oxide has a high melting point, boiling point? You say, no, because a lot of energy is required to overcome the strong electrostatic forces of attraction between the oppositely charged ions. Must mention about the amount of energy that you need. Is it very little or is it very large? And then how strong the forces is. So if so ionic compound usually have high melting point, boiling point. Means that the electrostatic forces of attraction must be very strong. And it exists between the oppositely charged ions. For electrical conductivity for ionic compound, we have to mention about two parts. One is in solid state. The other one is in molten or aqueous state. So in solid state, ionic compounds cannot conduct electricity. Okay, why is that so? Because in solid state, all these ions, the positive and negative ions, they are held in fixed position. Held in fixed position if it is a solid. Ions held in fixed position. So there is no charge that can move around to go and conduct the electricity. Hence, it cannot conduct electricity in the solid structure. Whereas in molten or aqueous state, as what we learned in kinetic particle theory already, liquid and molten state, liquid particles can move around freely, right? They are not held in fixed position. So I draw that move freely and then randomly. So in this case, the ions are free to move in liquid and solid, liquid and molten state. Hence, they is able to act as mobile charge carrier to conduct electricity because the ions are mobile and are free to move around to conduct the electricity. So remember, when you explain conductivity for ionic compounds, mention two parts: solid state and molten and aqueous state. One cannot conduct electricity, one can conduct electricity. Okay, then the next one would be the factor affecting ionic bonds. So we will only consider this factor when comparing melting point, boiling point between two ionic compounds. Because if both are ionic compounds, means both also have strong electrostatic forces of attraction, right? But how do we know which one is stronger? Then we have to look at this factor. And the first factor we'll look at would be the charge. So the larger the charge, the stronger the electrostatic forces of attraction. Because to have a very large charge, it means that I'm transferring more electrons. So the bonds between the positive and the negative ions are stronger. Whereas for radius, the larger the radius, the bigger the electrostatic forces of attraction. Okay, because when I have a very big radius, the charge is like distributed over a larger surface area. So effectively, because I have to distribute around a bigger area, then means that the electrostatic forces of attraction would be weaker because I have to cover a larger area. Commonly tested questions. So this is the example that I'm referring to. So I have a calcium oxide, which is an ionic compound because this is metal plus non-metal. So means that this is an ionic compound as well as KBr. K is potassium, Br is bromine. This one would be metal plus non-metal. So also ionic. So why would one be higher than the other? So it must be due to the difference between difference of one of these factors. Okay, means that the charge, could it be the charge? Let's look at it. For calcium oxide, the charge would be calcium because calcium is in group 2, so the charge would be 2 plus. Oxide ions would be 2 minus. Whereas for KBr is K plus and Br minus. So if you compare the charge, this one, calcium oxide, has a higher charge as compared to KBr. Okay, so this is factor number 1. With larger charge, it means that the electrostatic of attraction be stronger. So answer should be C, not D. Calcium oxide is not a covalent. Covalent, it means that we will only get covalent when we have non-metal plus non-metal. So not calcium oxide, because calcium oxide is metal plus non-metal, which is ionic. Okay, so that's for ionic. And then for covalent, Okay, so this would be the question that KJ asked about carbons, whether do they lose or they gain 4 electrons. So they don't gain or lose, they share electrons. And that is covalent bonding. So covalent bonding is only achieved when I have a non-metal plus non-metal. So for example, carbon dioxide, carbon and oxygen. Okay, so carbon has 4 valence electrons, right? And then it means that it will need 4 more electrons to achieve stable noble gas configuration. So in that case, carbon will share electrons with oxygen, so that in total it will have 8 electrons. So stable noble gas configuration around the carbon atom. So the words in this box means the number of electrons needed would be the same as number of electrons shared. So for example, like the carbon atom just now, carbon atoms initially only have 4 electrons, means that it will need 4 more electrons to achieve stable noble gas configuration. So in covalent bonding, if you need 4 from others, you will also need to share 4. Okay, so you can see the purple color crosses. Your carbon atom is actually sharing 4 electrons. And then so from the dot and cross, we can know what is the number of like single bond, double bond, triple bond. And dot and cross, in another way, it can also be represented this way. CO2. So one line represents 2 electrons. 1 electrons from oxygen, 1 electrons from carbon. Okay, so we need to understand like how to read this kind of structure. Okay, so this is for one covalent molecule. So if you have many covalent molecule, then we will get, this one I will just, we will get a simple covalent structure. So many covalent molecules. So many carbon dioxide. This will give us a simple molecular structure. So when we look at simple molecular structure, the bonds that we are interested in would be these intermolecular forces of attraction. So inter means like between, in between molecules. So when we are melting or boiling, we are breaking the forces of attraction between the molecules, the dotted line over here. Okay, some students will get confused and then they will think that, oh, it's the covalent bonds between the oxygen and hydrogen atom. Okay, but when we are melting or boiling it, we are not breaking this bond. Not breaking this bond during melting or boiling. Remember, when you explain later, a small amount of energy is required to overcome the weak intermolecular forces of attraction between the molecules. Okay, not the covalent bonds between the hydrogen and oxygen atoms. Okay, so similarly, also need to know how to explain why whether a simple covalent have high melting point or high melting point boiling point or low melting point boiling point, and why. So for simple covalent, because the intermolecular forces of attraction is weak, so I only need a low amount of energy to overcome the weak intermolecular forces of attraction. So generally, your simple molecular structure would have low melting point boiling point. For electrical conductivity, it does not conduct electricity because I don't have any charge carrier in my simple molecular structure to move around and conduct electricity. Okay, because for your molecules, everything is like neutral over here. But this is not charged, this is not charged, this is not charged. So no charge carrier. So although they can move around, but they are not charge carrier. So also cannot conduct electricity. Okay, then what is the factor affecting the melting point, boiling point of simple covalent? So just now for ionic, we have the charge and the radius affecting. For simple covalent, it will be the molecular size as well as the surface area of the molecule. So the larger the molecular size, the stronger the intermolecular forces of attraction, stronger IMF. Because the area, because the size is very big, so the attraction that they can form can be very big. But for smaller molecules like this, the intermolecular forces attraction that is formed would be weaker because the size is smaller, so the attraction that they can attract each other will also be smaller. So you can see I use a very short dash and a very long dash to represent a weak and strong IMF. For surface area, the larger the surface area, there will be a stronger intermolecular forces of attraction. Because I have a bigger area for me to form the smaller attraction. Whereas for this spherical shape, the surface area is smaller. So the area that I can form the intermolecular forces of attraction will also be smaller and hence weaker attraction between the molecules. Okay. Okay, I'm aware of the time, so let's look at the questions on page 51. Okay, I have an atoms Q and atoms R, and then they chemically combine to form an ionic compound. So it means that ionic compound means I will have metal plus a non-metal. So metal will tend to lose electrons, right? Because it's easier for them to lose 1 or 2 electrons than like gaining 6 or 7 electrons to achieve stable noble gas configuration. Non-metal would be the one that is gaining electrons. So you look at Q, it already has 7 electrons. So logically, it will just need to gain 1 more. So Q would gain 1 electrons to achieve stable noble gas configuration. Then it will have 8 electrons already. So if Q gain 1 electrons, means that it will become Q minus. And for R, the valence shell only got 1 electrons. So just nice, I can just lose away this 1 electrons. Then I will have a stable noble gas configuration. Lose 1 electrons, then it will become R plus. So if I have R plus and the Q minus, the formula would be RQ. Okay, is it okay? Any questions? You can type in the group chat if you have any questions. Then I will address your questions. Okay, for question 2, what would be the identity of elements W, X, and Y? Okay, so this one line represents 2 electrons. So if you look at W, total it has 3 lines. It means that W is sharing 3 electrons. Because this line you can imagine like there's a cross here, and then the circle comes from the neighboring atoms sharing. So sharing, why would W want to share 3 electrons? It means that it needs 3 electrons to achieve stable noble gas configuration. So if I need 3 electrons to achieve stable noble gas configuration, means that I will have 5 electrons initially. If initially I have 5 electrons, it means that this element W must be in group 5. So look at all the options here. So far, only nitrogen is in group 5. Carbon will be in group 4, aluminium in group 3. So we can eliminate option A and B. Okay, X is the same for C and D. How about Y? So Y, I have Y is sharing 2 electrons over here. So Y share 2 electrons. It means that it will need 2 electrons to achieve stable noble gas configuration. So if I only need 2 more, it means that initially I will have 6 electrons already. So I have 6 electrons initially. By the way, the 6 electrons that I'm referring here is 6 valence electrons, electrons in the outermost shell. Because only the electrons in the outermost shell will be shared. Electrons in the inner shell, they don't participate in any bonding. So since Y must be in group 6 or group 16, so it must be sulfur, which is in group 6. Hydrogen is in group 1 in the first column. So answer for this question will be D dot. For question 3, this one is the one that we have to look at the melting point and the conductivity to determine the structure of the unknown substance. Okay, so electrical conductivity at room temperature, if it conducts electricity, it means that substance X must be a metal. Okay, this one I didn't go through just now. So why metal can conduct electricity is because in your giant metallic lattice structure, which looks like it's arranged by, there's a metal cation ions, and then there will be these electrons, valence electrons that is lying around electrons. So these electrons, they are mobile, they're able to move around, so they can act as mobile charge carrier to go and conduct the electricity. That's why for metals, is able to conduct electricity due to the presence of the electrons. Mobile valence electrons. Okay, for option substance Y, it doesn't conduct electricity at room temperature. So this one means that this can be either be an ionic compound or a simple molecule, because it doesn't conduct electricity at room temperature. Okay, by the way, at room temperature, so your ionic compound will be in solid state because the melting point is very higher than room temperature. So means room temperature is about 25 degrees Celsius. If it's below the melting point, that means your ionic compound would exist in solid state. Okay, it's unlikely to be simple covalent, because if it's simple covalent, usually the melting point molecule will be very low. It will be like lower than 200. So Y must be an ionic compound. X must be a metal. And for substance Z would be a graphite. Okay, this will be under a giant molecular structure, which we didn't talk about today also. But diamond, it cannot conduct electricity. Cannot conduct. Graphite is also giant molecular structure. And is able to conduct electricity. Okay, this is something to do with the number of valence electrons that the carbon atom has that is not involved in covalent bonding in the giant molecular structure. So if you're interested, this would be on page electrical conductivity. Okay, or page 40 of the notes. Can refer to page 40. Okay, last question. Okay, I have sodium chloride with this boiling point and silicon tetrachloride with a significantly lower boiling point. So what could be the reason? Okay, so the high boiling point is actually telling us that this substance has a giant ionic lattice structure, giant ionic lattice. And so this one is a simple covalent because of the low melting point boiling. So for giant ionic lattice structure, the forces of attraction that we'll be looking at, like this, would be the EFA between the oppositely charged ions. EFA between positive and negative ions. For simple covalent, remember just now we have this simple covalent, and then the bonds that we are interested in is the intermolecular forces of attraction between the molecules. Okay, not the covalent bonds. So these are the two forces that we are comparing. EFA between the opposite charge ions and the IMF between the molecules. So which option is telling us this? Okay, option A will not be correct because talking about covalent bonds. Covalent bonds exist between the atoms, which is here. This is the covalent bonds. But when we are boiling or melting, we are not overcoming these covalent bonds. We are breaking the purple color one, intermolecular forces of attraction. So option A is out. Silicon tetrahydride having weak intermolecular forces of attraction. This one looks correct. Option C, why is it incorrect? Forming weaker bonds with chlorine than sodium. Okay, silicon with chlorine. So this one is between the atoms. So again, when we're looking at simple molecular forces of attraction, we are not looking at atoms. We are looking at the bonds between the molecules. So option C is also out. Then for option D, this one shouldn't be atoms. This one should be the oppositely charged ions. Okay, for question 5 and question 6, could you just screenshot the answer? And then you can look at it at your own time. Sorry to overrun the session. Okay, screenshot the answer. For the next question. And for question 6. Okay, so this one, although the molecules looks very big, but the question says molecule. So molecule is only for simple covalent structure. Okay, because it exists as a discrete molecule. If it's giant covalent structure, then it will be like an extensive network, like graphite, like diamond. Okay, but there's no more, this is not a network, this is just one single molecule. So the structure will be simple molecular structure. Okay, can take down the answer, do a screenshot or take a photo. So for part C, because both also simple covalent, a simple molecule. So when we compare, we will use the factor that is affecting the intermolecular forces of attractions to compare between two of them. And borylphosphine have a significantly larger molecular size than methane. This will talk about the energy, talk about the kind of forces, okay, whether it's strong or weak, and then the kind of forces between the molecules. Okay, thank you for listening to the end of the session. Okay, I hope you have learned at least something from this session. And before I end, could you please help me to do a review on this session so that we know whether like this kind of session is helpful to like your students or not. Okay, can scan this QR code and write about how you find about this session. When you write, please specify like which sessions you attend. Like today's this session will be Sec 3 IP Chemistry. And just write my name somewhere in your review. Okay, I'm teacher Sheila. So that my boss know like which teacher that you are giving your review to. Okay, if you are done with the review, then that's all for today's session. Thanks for joining. Okay, I hope that you find this session useful to you. Okay, KJ, I saw your questions. Why some covalent compounds more than 8 electrons in one atom? Okay, this is only possible for atoms that have has a vacant d orbitals. So for example, usually these kind of atoms, they will exist in period 3 and above. So if you look at a periodic table, it will be the third row and below. So let me show you. Give me a while. Okay, can look at the notes page 11. Notes page 11, there's this S block, D block, and P block, right? So for the elements in the D block, because the energy level of a 3D subshell is not so much of a difference as compared to 4S. So it's able to like go and occupy that subshells when is involved in covalent bonding. It is a special case like it's what we call exceptions to octet rule. And the reason is because it is able to access the 3D orbitals. If you want to find out about more, is in the notes page. Page 29 of the notes. There's some example to which atoms can expand beyond 8 electrons. Okay, thank you for the questions. Okay, I will end this session here. Thank you. Bye-bye.